So based on where we got with the East Coast, we basically spent a lot of time on the East Coast reviewing this. We made it farther on the West Coast this morning than we did on the East Coast. And so there's a chance that we'll finish. We're just going to see how far we make it, but you will undoubtedly make it farther than the East Coast did. What I'm going to do in order to complete the lesson for what I'm going to do again, in order for the East Coast to be able to see all of it, is I'm going to kind of clean all of this up. And again, I apologize, like coming home and all of that stuff. It's just, it's not as clean as I would like it to be. So I will basically do a video lecture of just myself walking through all of this. And I will make that available to you all. I may also do open office hours. We'll see. This weekend is quite busy, but I'd like to be able to maybe do that and go through time series modeling, just to provide more context and to go through this more thoroughly, or not more thoroughly, but go through it kind of as a recap after you've heard it the first time. So with that being said, what I want to focus on for this afternoon is I want to make sure that we're coming away with good and, as much as we can, solid conceptual knowledge. So I'm going to, rather than prioritizing getting through the material, I'm going to prioritize making sure that we've got a robust understanding of the basics, and we'll continue to build on that for as long as we have. With that being said, one note that I made to the East Coast and want to make to you all as a result. So based on where we made it on the East Coast, we will not include any content on the quiz beyond ARIMA modeling. So at the end, or after we get through ARIMA modeling, we talk about seasonality, fitting a seasonal ARIMA model, and fitting a multivariate time series model. These are important things to go through, and these are things that I would certainly cover in an online recording, as well as during open office hours if I can find time to do that this weekend. But that's sort of I just wanted to call that out now, so that as you are prepping for the quiz, you will want to get through the end of ARIMA models, but we may not get through all of this. And so wanted to just be clear about that. So, and actually I will set a reminder to myself to follow up in Slack or in writing to everyone later. Slack quiz, sorry, Max. Okay. So I will be sure to send that out, but I did want to verbally announce that at the top of the hour, when we're all together and are, fresh minds and all of that. So go ahead and you should be able to, you don't need to uncomment this again because fingers crossed, knock on wood, SciPy and stats models haven't upgraded since, 3 hours ago. But who knows? I was actually at a conference a while ago, and if it was like Pandas or something had updated that day and prepped the night before, and there was an issue, or there were updates that were pushed before my talk, which ended up not being a big deal, but created a lot of nerves. So let's go ahead and walk through this content. And as we walk through this content, just kind of recapping what we talked about this morning, and as we get into this afternoon, feel free to share any questions that you've got in the Slack channel. I want to make sure that we really, we really focus on that conceptual understanding, especially because we've got a little bit more flexibility here with respect to time. So again, we're dealing with bus ridership data and maybe some Portland precipitation data. So we want to deal with month-over-month data when we're forecasting the number of riders per month in the Portland bus system. This is in thousands. So one of the values was like 686 or something like that. That corresponds to 686,000. So go ahead, and I'm going to skim over. I'm just going to read in the data and do all of the data cleaning and editing that we had done earlier. So we should be able to get through Portland.index. And for me, that's cell 12. So let's go ahead and plot this raw data. So we plotted all of this bus data earlier, and we see the monthly ridership in thousands. Yes, Julia, we're going to get to selecting a value of P, absolutely. So we will absolutely go through that and we will spend a decent amount of time talking about that. So in looking here at the monthly ridership in thousands, we're able to see from 1973 to the middle of 1982, we're able to see this, the bus ridership in Portland. We see that these observations are correlated. Now, we sort of imply that they're correlated by doing a line plot instead of a scatter plot. But even if we had a scatter plot, there would be a clear pattern in our data. We see that our values are increasing over time. And we see that in addition to our values increasing over time, we see that there appears to be some seasonality. It's most obvious between 76 and 79. And that's something that we may want to take into account. So in terms of describing this, we might identify that the data are correlated. The mean is obviously increasing, and there appears to be some seasonality each year. This is especially apparent in the 76 to 79 window. So what I want to do is, this is something that we added on the East Coast when we were recapping this. And so the question was asked, what is stationary? And so what I want to do is, let me actually ask you a poll really quickly. So on a scale of 1 to 5, 1 being not at all, and 5 being you understand it, how comfortable do you feel with the idea of stationarity in time series data? Okay, so looks like a median score of 4. What I'll do is I will quickly run through these images. Then this is something that we did on the East Coast. So the question was asked: what does differencing do to our data, and how can we visualize that? And so remember that in the context of ARIMA models, we have to meet this one assumption called stationarity. So we need to meet stationarity. And there was a formal definition that involved the mean had to be equal over time. And in addition to that, the autocorrelation between 2 periods in time should only depend on how far apart they are and not anything else. So if I'm looking at 2 points, like 10 units apart, that relationship should remain pretty constant across all time. It should not change over time. It's not like early in time they have this relationship and then later in time there's this relationship. I want that to be consistent. And so an example of something that would not meet this, I'm going to actually go ahead and annotate on the slide here, or on the notebook. So I can draw. And so an example of something, actually let me exit that. I'm going to add in a markdown cell. Oops, turn that into a markdown cell and add a space and okay. So I'm just adding a little bit of white space here. All I did was I created a markdown cell, put 1 space in it, and then copy and pasted that. So I've got more white room. I can basically turn this into a whiteboard. So an example of something that is not, we'll do blue. An example of something where, to David Elliott's question, still fuzzy on that autocorrelation part, what we hope to see is something that looks like this. And that's, as we look at this over time, the relationship between 2 points in time appears relatively fixed. An example of something that would not satisfy that would be like this, where it's wide, and I have to draw with my trackpad, so I apologize for this, but then it kind of speeds up and looks more like this, and then maybe it slows down again. That would be an example of something where the left-hand side autocorrelation is constant, and on the right-hand side autocorrelation is not constant. Because we see that if we're looking at things 2 time periods apart here, they seem to have the same sort of relationship. Whereas on the right-hand side, if I'm looking at things 5 time units apart, that relationship is going to vary wildly depending on where we are. So what we want is, on the left-hand side, as Kenneth says, sine or cosine oscillations. We actually looked at a sine data example, just a randomly generated example earlier. So when we talk about stationarity and when we talk about what we want what is on the left, but on the right is something that is where that autocorrelation example is violated. So the question was, how does differencing fix this problem? And so we wanted to visualize it. What is differencing actually doing? Because we might know like the calculation that's going on, but let's plot it to see what it's doing. So I'm going to get rid of this. Well, no, can I clear it? Clear it. Okay, cool. So what I'm going to do is we generated this earlier. I'm generating a line plot of bus ridership. Above, we were looking at the actual bus ridership data. And we noticed that there's obviously not the mean here is changing over time. But if I scroll down to this, I'm plotting the Portland bus ridership data, but differenced by 1. So remember that .diff method is going to take YT and then YT minus 1 and subtract them from one another. And I'm plotting those values. So if we look at this, this is now what that monthly ridership looks like with a difference of 1. So we see now that mean is relatively constant. It's certainly not increasing like it was earlier. This is visualizing that difference of 1. However, we notice that in some cases, those oscillations are farther apart, and in some cases, those oscillations are closer together. And when we looked at that difference of 1, the p-value associated with that was like 0.19 or 0.11 or something like that. So basically, we could not conclude that this data was stationary. If we look at the difference of 2, it looks kind of similar, maybe a little bit better, but it's harder for our eyes to see it. And that's okay. We're not generally going to look at this using our eyes. We will generally just use the hypothesis test to do it for us. But hopefully this is helpful in terms of looking at what is actually going on. What is stationarity? So if you remember, when we iterated through the different values of the test, that hypothesis test, we looked at, or what we found was that a difference of 4 did have stationarity. So when we did a difference of 4, this data is stationary. It might not necessarily look that way to our eye, but it's a statistical calculation that we can rely on. So here it's, as we look at those oscillations, some are a little bit bigger and a little bit smaller, but by and large, they, to my eye, they look similar enough. This part gets a little weird, but by and large, this mostly looks the same. You'll notice that this tends to dip when we're looking after 1980. Remember, it was increasing until 1980 and then kind of leveled off or dropped off a bit. So we see that a little bit in this plot. But the point of these plots is to show you visually what's happening when we're differencing our data. And so if I look at this value here where my mouse is, that corresponds to May 1973. And so let's say that is -10. So what that corresponds to is we're saying that 10,000 fewer people rode the bus in May of 1973 than in January of 1973. If we moved here, let's say this is January of 1974, we're saying that about 150,000 more people rode the bus in January of 1974 than in December, November, October, September of 1974. So we have to go back 4 months because this is a difference of 4. Another question that was asked in the context of both a DM that I received and some students on the East Coast, they said, why do we pick the minimum possible difference? So when we're differencing that data, why do we difference by 4? Like, why did we break out? Why did we not continue looking at a difference of 5, 6, 7, 8, 9, 10 and pick something else? And there are 2 strong rationales for this. One is the principle of parsimony. This is a term commonly used in statistics. And all that means, the principle of parsimony, is that simpler models are better, all else held equal. We don't want a model that's too simple. Obviously, that suffers from high error due to bias. But if I have 2 models that give me the exact same performance and one is simpler than the other, go with the simpler model always. So as you think about, if you've got a model that's more complicated, but it performs better, go with the more complex one. But if you've got 2 models at like 85% R squared, but one is dramatically simpler than the other, or even slightly simpler, just go with the simpler model. So the question was, why do we stop at 4 here? So that's one reason. The other reason is looking at the data. So when I take my data, make a copy of it and shift it by 1. I'm creating an NA because when I'm trying in this top value here, when I'm trying to subtract one from the other, this value isn't subtracting anything because we shifted this down by 1. So there's not a partner there. So because of that, we're going to notice that the length of our observations will decrease. So here, if I look at the length of my Portland bus ridership data and I do a difference of 25, that gives me only 89 observations. Whereas if I look at the full series, that's 114 observations. So every time we difference, we lose 1 observation. And so if we can get away with using a difference of 4, let's get away with using a difference of 4, and let's not try looking to do 5, 6, 7, 8 or anything like that. So those are the reasons why we might stop at, those are the reasons why we will stop as soon as we get to that point. Once we get one value that's significant, we will stop there. So to sort of, we talked about our train test split. It is weird that this is not weird, but having that out of order and bringing that up before going into train test split. So to talk about what we discussed earlier this morning, kind of skipping over the train test split for the moment. As we're dealing with data, the first thing that we need to do in an ARIMA model is we need to assure that we have stationarity. And if we don't have stationarity, we need to get it. In order to get stationarity, we difference if our data aren't already stationary. So we're going to difference our data, and we want to difference by 1, then by 2, then by 3, then by 4. And the first time we get a difference that's significant, we stop it, we're done, we just pick that, and we move on. So that's kind of what we did this morning. Hovanes asks, could we say that the more we difference, the more degrees of freedom we lose? Yeah, because you're losing observations. So I don't know if degrees of freedom explicitly come into play here, but I believe that they do. If you're not familiar with degrees of freedom, like just to the broader class as a whole, it is basically the statistical term that determines how many free variables we have in a system. And the degrees of freedom are often important when we're doing calculations. And so we generally want to have more degrees of freedom, and we don't want to have fewer degrees of freedom. So it's just more flexibility in our model is the way that you can think of it. So the question that I have for you is, so in talking about stationarity, let me now shift to different. So Mark from Seattle, what about larger data sets where you can afford to lose data? Would we gain accuracy with D equal to 25? And you may. So depending on what it is you're predicting, if you want to try and, if you're measuring accuracy, R squared, whatever, you may be able to do that. And so you might just grid search over different values of D. In general, we go for the simpler model because A, it's more simple, B, saves us more data, and there's never a good reason to get rid of data if we can avoid it. And the other thing is that maybe differencing by 4 is more interpretable than differencing by 25, for example. Because we can say January to May, but thinking January of 2017 to February of 2019, that might not be as meaningful, in a clinical sense or in a practical sense. But you certainly could try it depending on what your goals are. If your goals are just to get the best prediction possible, which in many cases it is, sure, just grid search over values of D and see what makes the most sense. In more statistical settings, when you build these models out, with tender loving care, in that situation, you probably would want to go with the lowest value of D. But from a more, I'll call it data science-y perspective, where we tend to put a lot of things into grid search and just let it go, you could do that and maybe things would work out well. So in talking about differencing, so we know that we need stationarity in our time series data. And the way that we achieve stationarity, if we don't have it, is through differencing. How comfortable do you feel with differencing in time series data from a scale of 1 to 5? Okay, awesome. So we talked about the train test split, and the big summary of the train test split is that in the training set, the first set of our observations, time-wise, go into our training, and the last set go into our testing. The reason for that is that we want to build models and we want to be able to get an unbiased estimate of how our model might do in the real world. And so we want to use that latter data or the later data as that testing set. And so we can essentially use the training set and forecast forward. We'll do that moving forward. So we talked about the test set earlier today. Just going to run through those. So we manually created this. We had 91 observations in our training set and 23 in our testing. This gets to the point where, kind of to Mark's question, if you have larger data sets where you can't afford to lose data, then go for it. In this case, with our training model, we have 91 training observations. And so if we were to difference by 25, 91 minus 25 is below 70. Which means, it's not the worst thing in the world, but that can still be quite difficult. When we think about monthly data, this is data gathered over 10 years. So it's, it is difficult to come by that particular data or get data that might span much longer than 10 years. So we talked about the ARIMA model, and ARIMA stands for Integrated Autoregressive Moving Average Model. And there are 3 components to it. There's the differencing step, the autoregressive piece, and the moving average piece. So we talked about differencing. We need stationarity. Stationarity basically means that there just aren't systematic changes in our time series over time. And this sine curve, to Kenneth's point from earlier, this is a good example of a stationary time series. But when things aren't stationary, what we need to do is we need to make it stationary by differencing. We could check it visually, but that's really hard for us to do. Like the constant mean is relatively easy for us to do, but what's happening is that's relatively easy, but the trickier thing is autocorrelation. Assessing autocorrelation by eye is just challenging. So what we do instead is we generally rely on the hypothesis test, the augmented Dickey-Fuller test, which is a hypothesis test that will test for stationarity. We assume at the outset that our data are not stationary. And then if we have a small enough p-value, that means p is less than alpha, meaning we can reject the null hypothesis and then accept our alternative hypothesis, which in this case is that our data are stationary. So this, I'm going to remove this again because that is covered below. So we ran the augmented Dickey-Fuller test. We can import that as AD Fuller. And then Joseph Nelson wrote some code that will make this easier for us to interpret. In this case, our p-value is quite high, so we need to difference. What we did earlier was then we looked at these differences, delta t, and that's what we visually plotted above. And differencing will allow us to eventually get a stationary time series out of a non-stationary time series. What we do at that point is we're going to fit our ARIMA model to the differenced data. So we're going to start with a difference of 1 and iterate upward until we find that value of d that makes our time series stationary. You could try and grid search, although that can be more challenging. So write a for loop to find the lowest difference value d. This is a bit more extensive than what we did together, but the only distinction is we added in a counter that says we're checking this particular distance. And then our p-value here was, we get to see the p-value at every output. We're not just getting to see this one output. So if you run this, it says checking a difference of 1, and our p-value is like 0.198. We checked d equals 2, like a second order difference. Our p-value is 0.11. A third order difference, we got 0.197. And then our fourth order difference, we got about 2%. So differencing our time series by d equals 4 does yield a stationary time series. So moving forward, as we generate autocorrelation and partial autocorrelation plots, we're going to generate these plots of the differenced time series, not the original series. So we are no longer really working with YT. We're now working, and we'll use YT below, especially in cases when we don't have, when we're not differencing, but like you'll see in the notation, I'm still calling it YT, but really it'll be delta T. We're now looking at that difference moving forward. However, I kept it YT because that's what you'll see online, and that YT, like if your data were stationary, you would just directly work with YT. So the three pieces to ARIMA modeling, there's the differencing step, the autoregressive piece, and the moving average piece. So we've wrapped up the differencing step. At the moment, nobody's typing, so I feel like there aren't questions at the moment. I will take a swig of coffee for a moment to see if there are any additional questions. Okay. Now let's move into the autoregressive piece. And we kind of wrapped up the lesson talking about this, but it's good for us to get more into detail with it. And we can answer Julia's question about how exactly do we pick a value of P. So the next piece to ARIMA modeling that we'll cover is the autoregressive piece, which is commonly abbreviated AR. We talked about what AR is, or this autoregressive piece. Autoregressive means that we regress a variable on itself. And auto just means self. And this is something that we are able to, that we see come up all over the place. So autoregressive means we regress a variable on itself. Pretty straightforward. What this autoregressive piece does in the context of the ARIMA model is this is going to be responsible for modeling those long-term trends in our time series. So if I want to see the changes in crop yield over time or the relatively steady increase of employees, then an autoregressive model is probably most appropriate here. The autoregressive piece doesn't handle random sudden shocks. So you can think about scandals within an organization. You can think about like an oil crisis that just suddenly happens, or if there's an international political issue or the housing bubble bursts or whatever. There's all these different examples where autoregressive models don't handle those random or sudden shocks. So the autoregressive piece will learn regression coefficients on each of those lagged values of y that we're predicting. So an autoregressive model of order 1 will include one previous value of y. An autoregressive model of order 2 will include two previous values of y. And an autoregressive model of order p will include p prior values. So we could have all the way up through yt minus p, where p is the number of values we want to put into our model. So before we wrapped up, I asked, how do you think we might check, or how do you think we might decide on a value of P? And in short, we might use our autocorrelation plot to see what values seem to make sense. So we generate our autocorrelation plot. And this autocorrelation plot, actually, let me ask you, what might you interpret from this plot? Go ahead and respond in a thread, or in the thread. What might you interpret from this plot? Okay, so David, Manu, and Julia call out that certain lags appears to be significant, or certain lags appear to be significant. So for example, we're looking at a lag of 1, and to remind us, this lag means if I were to take yt, make a copy of it, shift it down by 1, and compare those, calculate the correlation between these two series, the value here is about 60%. In this situation, I'm looking at the correlation coefficient between these values. This will not work. We will get an error because as we shift this by 1 and we drop the NAs, these are of unequal length. So this does not work as is. I imagine that there is that's tutting. I have no idea what that is. As we look at this, what I would imagine that we could relatively easily fix that. I don't know off the top of my head of what that is. It's a dance thing with your hands. Oh, I don't. Now I'm self-conscious and have to just put them in my pockets for the rest of the lesson. It'll suck to type, but I guess this is the way that it is now. No, I'm just kidding. So Mark from Seattle asked, let me get back to you in a moment, Mark. Let's finish talking about this plot and then I'll answer your question. So as we're looking at this plot, we see that there's a lot of lags that are significant. For example, one of the lags that's significant is a lag of 1. So I'm looking at my bus ridership data and bus ridership data with a shift of 1. And actually, to clarify, this is a little bit inaccurate because what we're looking at here is the train bus ridership diff 4 drop NA. So in fact, the East Coast did not flag this earlier. In looking at this, we would realistically want to, we'll run into the same error, but we would want to do a diff of 4. So we'd want to compare those columns and look at the correlations among them, or the correlation among them. And so if we were to correlate those columns, the value should be right around 60% based on this data. The correlation between y, or I should say delta t and delta t minus 2 is about 30%. So this is how we're going to be able to interpret that. We can look at the correlation between our data and shifted or lagged versions of that data for lags 0 through 30. And that's what this visual here is telling us in the autocorrelation function. And this autocorrelation function is going to be important when we want to determine the value of P and the value of Q, which we'll talk about the value of Q in a bit. Okay, so in looking at this particular data, what we want to do is this is just a visual representation or a tabular representation of what those correlations are. And this kind of contextualizes that plot above. One other thing that you may interpret from this plot, Steve from San Francisco says there appears to be like the seasonality in the data or the cyclical effect. So if I scroll up, you can see exactly that. So our YT is strongly negatively correlated with like 6 months later, but is positively correlated with 12 months later, negatively correlated with about 18 months later, positively correlated with 24 months later. So it absolutely looks like there is it absolutely does appear that there's seasonality in this data. So this is something that we can use if we want to fit a seasonal ARIMA model. So I think close to where we wrapped up is what might be a downside of relying solely on this plot. And the idea is that if Y is highly correlated with a lag of 2 or a lag of 3 or a lag of 4, there's going to be all of these correlations in that itself. So Y highly correlated with Y, T minus 1, and T minus 2, that probably means that T minus 1 and T minus 2 are also correlated with one another. And so to get around that, we use the partial autocorrelation function, which is just a tweaked version of the autocorrelation function where, as I look at each new value of autocorrelation, it is now controlling for all lower order lags. So where my mouse is right here, this appears to be a value of 9. It looks like if I look at the correlation between YT and YT minus 9, if I take into account YT minus 1, T minus 2, T minus 3, everything in between, there's still a really strong correlation between our original data and a lag of 9 months. So we can interpret the partial autocorrelation plot here in a similar way. Notice that the blue band takes on a different shape, but that still represents our 95% confidence interval for the data. So anything outside the interval would still be significant. So to connect with Julia's question, how would you interpret the partial autocorrelation function here? Or sorry, how would you determine the value of P based on the autocorrelation function and the partial autocorrelation function? So there's two prongs to what we'll check. First, let's check to see if the partial autocorrelation function has a sharp cutoff. The second thing we want to check is, what is the autocorrelation function value for the first lag? So if the PACF has a sharp cutoff, and if lag 1 in the ACF has a positive value, we're going to pick P to be the lag in the PACF before the cutoff. So let's walk through this together. If the partial autocorrelation function has a sharp cutoff, if I look here and I move from 0 over to the right-hand side, so I look from 0 to 1, in this case, I'm not going to call this a sharp cutoff. And the reason that I'm not going to call this a sharp cutoff is this is always going to be 1. And what comes next is it's always going to be less than 1 unless we're dealing with just like an infinite set of copies of the same exact data. So as we're looking at this, what we want to take away is, I'm going to say here, going from 60% to negative 10% definitely represents a big drop or sharp drop off in that data. So I'll say check. Yes, the partial autocorrelation function does have a sharp cutoff. The second thing is, let's check to see if the lag 1 in the ACF has a positive value. So I'll scroll up to the autocorrelation function. The autocorrelation function plot, this value here is positive. So this is a positive 60%. And what we want to do is, because of this, we can say the partial autocorrelation is that did have a sharp drop off, and this value here is positive. Because of that, we then can move on to the next point here, which is then we choose P to be the lag in the partial autocorrelation function before the cutoff. So we look at where that big drop occurred, and it was in between lags 1 and 2. Because of this, we say, let's fit a model with a lag of 1, or rather P equals 1. So the way that we determine a value of P based on the ACF and the PACF is check the PACF for a sharp cutoff. If it has a sharp cutoff, check the first lag ACF to see if it's positive. If that's also yes, then go back to your PACF, P for PACF, and choose P to be the lag in the PACF before the cutoff. So because of this, we see the PACF does have a sharp cutoff between lag 1 and 2. The first lag in the ACF is positive. Therefore, we should set P equal to 1. So the question that I have for you here is, so Mark, won't the first value always be correlated to itself, and won't these rules always hold true? So the first value, we expect it will probably be correlated with itself, but if there's a lot of variability, or let's say that we were modeling a time series, like instead of looking at month over month, we're looking at 6 months over 6 months. So we're looking at like winter, summer. In that case, based on the period, we might expect there to be a negative relationship. Or if we were looking at the, number of cars going through a toll road, like between noon and midnight, or midnight and noon, or something like that, or like between 6 and 6 a.m. to 6 p.m. versus 6 p.m. to 6 a.m. That might be an example where they wouldn't actually necessarily be correlated. In this case, because a full season or a full period in this case is probably 12 months, and we're looking at smaller chunks of those, then sure, we would expect them to be highly correlated. But if we split the year up differently, just winter, summer, we might expect them to be inversely related. So this is not something you have to memorize, in terms of determining the value of P based on the ACF and the PACF. This is a good reference. This is something that I want you to be able to refer back to, but this is something that you should that you should be able to reference, like as you're working on a lab or as you're doing your capstone project or something like that. But hopefully this makes it a little bit clearer. So based on this rule here, if the PACF has a sharp cutoff and lag 1 value is positive, then this is how you choose P. So based on that, how comfortable do you feel with the idea of selecting P in time series data? Go ahead and respond to this thread. And as you have any questions, please feel free to throw them in here. Okay. So Manu asks, what if we do if these conditions aren't met? So if the PACF does not have a sharp cutoff, that is, if it's like a gentle slope and we say, you know what, it doesn't look like there's a sharp cutoff, or if the lag1 autocorrelation function value happens to not be positive, then we're going to let P equal 0. So in that case, we would just select P equal to 0, which, as we'll see in a moment, is basically saying that P is, or the autoregressive component is not part of our model. Yeah. Okay. So now what I want to do, now that we've talked about ARIMA models for almost 3 hours, I want to actually fit an ARIMA model. So again, there are 3 pieces to ARIMA modeling. There's a differencing step, and that's how we determine D. There's an autoregressive piece, and that's how we determine P. There's a moving average piece as well, and the moving average piece is something that we're going to talk about in a bit. We haven't covered it yet, so I'm going to fit an ARIMA model, just not focusing on the moving average piece, but just focusing on the first 2 pieces. Then we're going to bring in that 3rd piece. So we will import our ARIMA model. We can import that ARIMA model from statsmodels.tsa for time series analysis, .ARIMA model. We'll import ARIMA from that. ARIMA has to be capitalized. So we're going to, in this next step, we're going to instantiate our model. And in instantiating our model, we are going to, I just want to draw like a comparison between sklearn and stats models. Remember that during GLMs, when we were working with stats models, one of the things that we noted, one of the differences was that in stats models, we need to pass our data in when we instantiate the model rather than when we fit the model. So that's one difference between stats models and sklearn. So we are going to do that here. The information that we pass in, I'm going to instantiate my ARIMA model. I'll save that as model. I'm going to pass in 2 arguments. The first argument is ENDOG. That is short for endogenous variable. Endogenous is a social science term or an econometrics term that's used to refer to the Y variable. So that is our Y variable of interest. The order is going to refer to the values of P and D and Q. So in this case, I'm specifying P is 1, D is 0, and Q is 0 as well. So I want to kind of call something out here because this is a bit of an annoying thing. So what you'll notice is that for my endogenous variable, I fit the differenced version of my bus ridership data. However, in general, we should be able to fit this model, just getting rid of that. So getting rid of the difference, and then specifying here that our order is equal to 4. So we can just pass in our Y variable without manually changing that, and we get our order of 1, 4, and 0. So if I run this, I get an error. This value error, it's thrown in that order argument, and it says D greater than 2 is not supported. So infuriatingly, in this current version of stats models, you cannot difference by more than 2 because it won't work. However, we can manually work around that by saying, you don't need to do the differencing for us. We're going to difference our Y variable automatically. So in order for us to fit a model where we're going to difference with a D value of 4, if I scroll up, instead, I'm going to say, let's change this train bus ridership data to be by 4, and we drop our NAs. And then I change that differencing order to be 0. So that's what we are going to do here, because we're going to manually difference that data, despite it being a little bit annoying, because only certain values of D are supported. If you had a value of D that was like 2 or 1, should work, but stats models is finicky and it's not kept up nearly as well as sklearn. In addition, just one of the notes about stats models versus sklearn. Stats models is much more statistical in nature, and because of this, it does require a lot of statistical expertise to be able to program the algorithms behind fitting this model. We're going to see that the moving average piece actually is really, really, really challenging to fit. The algorithm is not as easy as like gradient descent or something like that. And so with that, we it's just sklearn is much better maintained than stats models. Now, sklearn doesn't have this, so we're sort of, I don't want to say stuck with stats models, but one recommendation that I will have is if you really need to do time series analysis, this ARIMA model is probably not as good as the SARIMA model or the SARIMAX model that we're going to see later. We're going to see that later. However, one other recommendation that I have for you is to use R, because Python is just not as well equipped for that advanced statistical stuff. So if you say, look, I need to do research, or I need to be able to build out like professionally build out a model in R or something like that, or build out a time series model, then you'll want to build that out in R. So in fitting this model, you can go ahead and fit that model. Or sorry, not fit, we've instantiated this model. So we instantiate it, but again, that distinction is we pass our data in here. We can fit our model, so I'm doing model.fit. I'm setting that equal to ARIMA 140. We call this an ARIMA 140 model because P is 1, D is 4, and Q is 0. So we fit that model. And then if I want to generate predictions, by default, it's going to generate predictions on the same range as the training set that we passed in. So I can save that as preds. If you want to check out the first few values of preds.head, we'll do that. And my question for you is, what do these predicted values represent? So in terms of the predicted values here, what do these represent? Yeah, so the predicted values here are going to correspond to those differences. Those predicted values are not going to be modeling Y directly, but instead those differences, those 4-month differences. And we can see that, like it should be relatively obvious to us if we look at this data, or we just have a really bad model in the sense that we're predicting, only 1,900 people are using the buses the entire month of June, or negative 14,000 people are using the buses in September. So that would be a bad model. And not saying that our model is necessarily good. However, we can, what these mean, the other giveaway is that this is starting at May instead of starting in January. So this value for May corresponds to, there's a 32,000 rider increase predicted in May relative to January. So more people are taking the bus in May than in January, but about as many people are taking the bus in June as in February. So that's how we would interpret these predicted values. So they represent delta t hat. So those predicted values for delta t, that difference. Again, this is just saying in text what I just verbally said. These represent the first predicted value, or the first observation represents that 4-month difference. One thing that we can do with this is we can plot this data. So what I've got here is I'm plotting my differenced data, and then I'm plotting my predicted value. So here I'm comparing my predicted values on my training set and the training set itself. But if I look at this, this is our bus ridership with an ARIMA 140 prediction. So it's interesting to look at this. This might look really good, and it's interesting. If you were to put like just a time variable in a multiple linear regression model instead, like a 1 unit increase in time corresponds to whatever unit increase in bus ridership, we'd get like a flat line for that time. But this obviously varies a lot more. So in looking at this, this looks good. It actually isn't that good if we model it or if we evaluate it. So we can evaluate it using mean squared error. So if I look at the mean squared error here between the training data, the difference training data, and our predicted values, our training or our mean squared error, even on the data that's fit on, it's off by like 51,000 or 5,100, but the data are in thousands. So that's actually 5.15 million. Mean squared error is weird to think about. So you can calculate root mean squared error, but even with root mean squared error, we're off each prediction on average by 71.8 thousand. The reason or there's a couple of reasons for it. One, we've built like all things considered, a relatively simplistic model. We haven't added a seasonal component to the model. We haven't added an exogenous predictor to the model. So we haven't done that. In addition, the values that we have here, they take on the same type of shape, but the orange looks shifted a little bit to the right of the blue. So like the peak here is a little bit to the left of the orange peak here. So it looks like it's lagged just a little bit, which is perhaps unsurprising. So maybe we want to fit a different model. So a couple of things that we can do. We talked about adding in a seasonal component. We talked about adding in a set of exogenous predictors, and we also haven't looked at the moving average component yet. So that's something that we would want to do. So there's a lot of improvements that we could make to this model. But yeah, so as Kenneth calls out, the curve is clearly not smooth here, but that's somewhat okay because the actual data that we're working with here are not smooth. Okay, so to wrap this up, the model that we refer to this as is an ARIMA 140 model. And I said this verbally above when we instantiated our ARIMA model. But in general, we parameterize our ARIMA model with P, D, and Q, where P is equal to the number of autoregressive terms in our model. And we determine that by looking at the ACF and the PACF of our differenced data. D is the order of differencing we found in using the augmented Dickey-Fuller test. And Q is what's coming up next. So there are 3 pieces to ARIMA modeling. There's the differencing step, there's the autoregressive piece, and there's the moving average piece. We've not gotten into the moving average piece, but that's what we're going to come up with after the break. It is 56 after the hour. Let's go ahead and let's come back at 7 minutes after the hour. So for the recording, you asked, so would we normally do all 3? It seems like overkill and we would lose a lot of variation. The answer is yes, we would do all 3 in some cases. And it depends on what the data dictate or what the data sort of imply that we should do. But what we are, in looking at this, it's very possible for us to overfit, but we want to evaluate our model on our test set, and we can do all of this because we're trying to forecast something forward, and we need a model that's appropriately complex. We need a model that can take past data and predict forward, and it's going to vary sort of with that past data. So, it's something that we could do all three, and we generally would. When we fit the model, we're always going to check the value of P and D and Q. Now, in some cases, maybe the value of P would be 0, or maybe the value of Q would be 0, or maybe the value of D would be 0, which makes our data or our model simpler. But if we're modeling a complex process where we're looking at how things vary over time, if we want to extract a seasonal component, which we haven't even talked about yet, or adding in another variable, there are a lot of things that can go into play here. So what we're going to do is we want to finish up talking about ARIMA models. There's a differencing step, an autoregressive step, and a moving average step. And you will want to go through all three of these steps every time you fit a model or fit an ARIMA model, unless you go with like the grid search option, which you could. But as you do this, it's important to go through all three of them. Maybe you end up with a simpler model. So that differencing step corresponds to D, the order of differencing we found using the augmented Dickey-Fuller test. The value P, the number of autoregressive terms in our model, is going to be based on, or that determines the autoregressive piece, and that will be based on looking at the ACF and the PACF. And then finally, let's talk about the moving average piece, or the moving average component to this model. The final piece to ARIMA modeling that we'll cover is the moving average piece. We often abbreviate it as MA. And this is a little bit different. So for autoregressive models, or for the autoregressive component, what we did was we fit our Y variable, or we regressed Y on other values of Y, like earlier values of Y. In this case, we have a moving average process, and we're going to regress Y on these errors. So, for example, a moving average process with order 1 or of order 1 will regress Y on one prior error. So we've got this mu that should be the mean of our time series, similar to beta naught, but the notation is generally mu for moving average and beta naught for autoregressive, even though it all comes out in the wash. But we're going to regress on one error here. So the error is the epsilon value for t minus 1. So I don't want to draw an explicit connection between this and boosting because they're not related, like not directly related. But remember that when we looked at boosting last week and you fit like a random stump or a decision stump, as I think a couple of people said. And so you had this really short decision tree. You fit that to your data, and then you went ahead and looked at how well your predictions were. Some things you predicted well, some things you predicted poorly. So then it reweighted your observations based on what you predicted well and what you predicted poorly. And it upweighted the things that you predicted poorly so that when you fit the next decision stump to it, it would be able to better target those errors. So it would focus on the things that you'd gotten wrong with your first tree. You do this process over and over and over again. That's sort of similar to a moving average model where we are regressing Y on our past error terms. What this does is as we think about the number of errors we want to incorporate, this allows our moving average model to handle sudden shocks well. So the autoregressive piece didn't do that, but the moving average piece did do that. And so the moving average piece will be able to handle, a wildfire or an overly rainy season that affects your crop yield, or when dealing with a massive layoff or acquisition or whatever, if you're modeling the growth of your company, which is the example or a couple of examples that we talked through earlier, the moving average component is going to be able to handle that. So as a technical note that you may or may not be interested in, this is like a bonus. It is certainly not need to know, but as a bonus here, because those error terms or those epsilons are unobserved, we have to rely on more advanced algorithms to fit that model. So it's not as straightforward as looking at our Y variable and then creating a copy and shifting it. Instead, we have to look at, we have to basically iteratively fit this model, is my understanding of it. There's a paper on the topic here if you're interested in reading that. It's not need to know, but that's something that you might consider looking at. If that's something that you're interested in understanding how you would find, or how your model rather would find the coefficients of that model. I'm sorry, I'm feeling so poorly now. So moving beyond the moving average piece, or how do we use this moving average piece in the context of the thing that we want to be able to understand, or the thing that we want to be able to do? So we want to be able to determine a value of Q based on the ACF and the PACF, kind of like we did earlier. So when we were dealing with the value of P, we wanted to figure out how many values of P, or how many prior values of Y we wanted to put into our model, we turned to the autocorrelation, the partial autocorrelation function. In this situation, we are going to refer back to the autocorrelation and the partial autocorrelation, or we'll look at kind of a similar set of things. But in fact, even though this says we're going to base it off of the ACF and the PACF, the only thing that you need is actually the ACF to determine Q. So if your autocorrelation function, if your ACF has a sharp cutoff and your lag1 ACF value is negative, then we're going to choose Q to be the lag in the ACF before the cutoff. And so this is the same sort of thing that, this is the same sort of process that we went through when determining the value of P. We're just doing the same thing with Q. The difference, or there are two differences here. First, for P, we looked at the partial autocorrelation function. For Q, we're not going to do that. For Q, we just look at the ACF. The other thing is that for P, we needed to check to see if that lag1 ACF was positive. Here, we're checking to see if that lag1 value happens to be negative. So to emphasize that again, P is determined by the lag in the PACF. The P matches up there, which is helpful. The P's match up there, which is helpful. Q is determined by the lag in the ACF. If the ACF doesn't have a sharp cutoff, or if the lag1 value is not negative, then we're going to set Q equal to 0. So basically, if either of those conditions are not met, then we're going to let Q equal 0 and just move on. So based on the ACF and the PACF, what value of Q might you select? So let me go ahead and scroll up and look at let's look at this. So first, if the ACF has a sharp cutoff. So I'm going to scroll up to the autocorrelation function. So in looking at the autocorrelation function here, we have our value of 1. That's always going to be 1 because we're looking at the autocorrelation of a series and itself. The next value is 0.6. So we've got the autocorrelation, the correlation of YT and YT minus 1, and that is 60%. Let me see, 30%, 5%, negative 30%, and so on. So do we have a severe drop-off or a dramatic drop-off here? Well, it depends. So basically, well, it does depend. That is the correct way of saying it. It depends. And there's not a hard and fast rule. This is one of the most infuriating things about it. I wish that there was a hard and fast rule that would allow us to say if it changes by this much, then that's what it's going to be. But in this situation, we're looking at the autocorrelation function and looking at a drop of 60% to 30%. Maybe that's a sharp cutoff. Maybe 30 to 5% is a sharp cutoff. It could really go either way. If I have to pick one area, if I say, yes, there is a sharp cutoff, I'm probably going to look at the gap between 2 and 3. The reason for that is even though the actual number dropping from 60% to 30% is larger than the gap from 30% to 5%, I'd probably say this is a more dramatic drop, especially because you're going to expect some randomness around 0 anyway. So I think that's probably the more dramatic drop, but it's, realistically, what I would do is if I was fitting this, is I'd say, let's check this gap, let's check that gap, and let's essentially grid search. Let's try both of them and see which one does better. So that is ultimately the way I would go about doing this. So that's the first condition, is there a sharp cutoff here in the autocorrelation plot? Note that we're using the differenced autocorrelation plot here. And in that differenced autocorrelation plot, we see maybe there's a sharp cutoff, but maybe not. So we can check out that gap, maybe not, we'll see. So let's scroll down to the other thing that we need to check out. So if I scroll down to how to determine Q, the other thing we look at is the lag 1 value in our autocorrelation function, is that negative? So let's scroll up to see if that value is negative. Well, I mean, we just saw that value, but scrolling up here, we look at the partial autocorrelation, the autocorrelation, not the partial. We look at the autocorrelation function, and that first lag value is positive 60%. So that's definitively not met. Well, remember, if either of those two conditions are not met, we set Q to be equal to 0. And so in this case, it doesn't matter if there's a gap here, because that first order difference does happen to be positive. We're going to set Q equal to 0. So I'll go ahead and scroll down. In this situation, I would go ahead and set Q to be equal to 0 in this situation, because our lag 1 ACF value is not negative. So if I remember correctly, there's a couple of mistakes in here. Oh, no. Okay. So this is the updated version. So based on the ACF and the PACF, we could say the ACF maybe has a sharp cutoff between lag 1 and lag 2, or maybe between lag 2 and lag 3. It depends. But the first lag in the ACF is positive, and that just kind of makes the decision for us. We're going to set Q to be equal to 0. And as a note or as a reminder, even though this question says based on the ACF and the PACF, it's sort of like a trick. The PACF does not determine that value of Q. So when you're looking at the value of Q, you only look at the autocorrelation function for that. If you were happening to look at, if you went back and were looking at the like the other starter code, I can share this code or that that text with you. Several people are typing, so I want to give you a moment to type. Thank you, by the way, Julia. Remy, if the lag 1 ACF needs to be negative, when would that ever not count as a large cutoff? A drop between 1 to any negative number seems like it should qualify for a large cutoff. It could, or that does seem like it would qualify, but so when I look at the autocorrelation, I'm going to scroll up. I mean, I don't know if it's appropriate, and I probably should explore this more, but I don't think that it's appropriate to look at that gap, because this is always structurally, like by default, going to be 1 or required to be 1. So everything's going to see a drop there. I think that actually looking at the data, I think that's more informative. So you're absolutely right. If that were to happen to be negative, that should qualify as a sharp drop. But in general, I start looking here where that lag is 1. And then, look from 1 to 2, 2 to 3, 3 to 4, and so on. But you are correct. That should qualify for a large cutoff. But I just ignore that 0th value because it's really just there for decoration, effectively. So as people are typing, I'm going to scroll down and we can continue. Steve, does this mean that if the dependent variable is not negatively correlated with the first order error term, Q should be 0? So does that mean that if the dependent variable y is not negatively or is positively correlated with the first order error term, Q should be 0? Yes. So if this, in this situation, if this value we see this, that's not negative, so that's positive. So because this is positive here, then Q should be equal to 0. Yes. So if either of those conditions aren't met, if there's not a sharp drop off, or if this is positive, you set Q equal to 0. Will from Denver. So if lag 1 was negative, would you set Q as 1? So it's weird to talk about that because if I assumed that that was negative, then I'm not sure like what those values were or what would qualify as a steep drop. But if I was looking at this, I would either pick Q to be 1 or I'd pick Q to be 2, just because of those drops or those movements towards 0. What you could do is basically fit both, see which one happens to fit your data better, and then, evaluate on your test set. So it's almost like a manual grid search by seeing, looking at that gap. And then, so in this case, I would set Q as equal to either 1 or 2, try both, see which one is better. If they're about the same performance, then I'm probably going to go with Q equals 1 because that's an easier or a simpler model. And that gets back to that principle of parsimony, or the idea that we just want all else held equal, we want a simpler model. And so Remy asked a question in the thread to his initial question. Okay, so the first effective value needs to be negative, and what we're looking for is a large absolute value change from that. Yes, we want to look for a large absolute value change from that first value. And in general, we want to look at that change closer to 0. So when we talk about like a drop off, we want it to be closer to 0. Or I guess if it changes sides, then that would be okay too. Shoot, now I have to think about that. Because I mean, that's not something that comes up super frequently off the top of my head, but you could, I'm sure you can construct a situation with that. And I want to figure out what that would be. So yes, in general, you'd want to see the gap from, you want to see this, and if it goes to 0 or on the other side of that. So sure, we'll say an absolute value change away from that. If it was more extreme in like the positive direction, I don't know if I'd call that a drop off. So it went from like 1, here was 0.6, but then this value here happened to be like 0.9. I don't know that I would necessarily do that. So Mark, lag equals D, Q, or K, depending on the step of the algorithm. Yes. So time series modeling is very, it's very statistical and very like, deliberate in nature. I kind of wish that wasn't the case. And what we could do is we could just try and automate it by like doing essentially a manual grid search by like nested for loops. And there's some code down below that'll do that for you. But if you do this like properly or the right way, you will, you identify D first, then P, then Q. Or I guess P and Q can be done simultaneously. All right, so let me go ahead and scroll back down. Okay. So so in this situation, to kind of recap the important takeaway of this, the autoregressive piece is going to focus on modeling long-term trends in our process. The moving average piece will be appropriate when we model sudden fluctuations in our process. So if we notice there are sudden changes in the process, if we notice that there's a scandal, or there's like at a company and that changes their stock value, or there's major political shifts, or something happens, like Lyft had their IPO, Uber joined, or Lyft just had their IPO, got their stock price. Lyft had their IPO, there is a stock price for Lyft. If Uber has an IPO soon, then that Uber IPO might dramatically change the impact or change the value of Lyft's IPO or Lyft's stock price. And so based on that, you might say like, oh, that's an example where, we've got these sudden fluctuations, and having a moving average component to our ARIMA model, we'll be able to more quickly bounce back from that. Whereas the autoregressive piece generally does not bounce back nearly as quickly from that. So pulling these pieces together. To reiterate, there are 3 pieces to ARIMA modeling. There's the differencing step, there's the autoregressive step, and there's the moving average step. And many times we're going to see time series data that has both long-term trends and sudden fluctuation. So we want to combine these together into one model. And that's obviously what we've been building toward. An ARIMA model is going to consist of both an autoregressive and a moving average component, or we would describe it as potentially having that. So we can talk about some examples where we see both long-term trends and sudden fluctuations in our data. Stock prices, stocks are going to change over time, but there's news that might dramatically affect them. When you find out that Amazon is acquiring a new company, or any organization like Google or whatever is acquiring a product, that sends ripples through the markets because that price might go up and the price of other things might decrease. Gas or oil prices, same kind of logic as stock prices. We're going to see smaller changes in gas and oil prices, but what will end up happening is beyond that, you'll notice that that there are international events and things like that that may, that will obviously have an impact on those. And public transportation ridership. So we imagine that public transportation ridership will probably be slow over time, but you might have a marketing campaign. You might change your price. You might have an accident. An example, unfortunate as it is to think about, is the impact of, so the example is thinking about 9/11. And if you were to try and track the change in transit, specifically airplane transit, in the months following that, I would imagine that you would see probably a dramatic drop in that, at least over time. And so the accident, or accidents like that, or terrorist attacks or something like that, might have a sudden unforeseen shock on ridership. And that's something that you may want to, that's something that is important to note. So when we're dealing with time series data, and kind of to the question here Hovhannes asked earlier, would we normally do all three? In this case, the answer is yes, because in many cases, there's a lot of different things affecting it. There's both a long-term trend and there's sudden shocks to that. And we want to be able to bounce back from that more quickly. So when we talk about an ARIMA PDQ model, we specify it by how many lags we're regressing Y on, how many errors we are regressing Y on, and how many differences we need to calculate in order to achieve stationarity. So we regress Y on P prior values of Y. We regress Y on Q prior errors in our data. And then, and before all of that, we set up how many differences we have. So D is going to be how many differences do we calculate in order to achieve stationarity. So putting it all together, I'll zoom in so that we can see this a little bit better. An ARIMA PDQ model is going to be equal to modeling that difference, YT minus YT minus D. So what's that difference? In the data we had above, D was equal to 4. And that's equal to an autoregressive model of order P plus a moving average model of order Q. And so we literally just add them together. And this is what, if you were to write it out, that looks like. This is, scary is probably not the right word to use, but this is, this is a nasty looking formula, which is why we sort of built up to ARIMA rather than just kind of throwing that formula out there at the beginning. But depending on the values of P, D, and Q, we might refer to these models by different names. So if, for example, D were to be equal to 0, we don't have an integrated piece. That integrated piece where that difference comes into play, we don't need to worry about that. Or if MA is equal to 0 and D is equal to, or, if like, for example, D is equal to 0 and Q is equal to 0, we say it's an ARP model, or an autoregressive model of order P. So basically this piece drops out and the difference piece here drops out. So we would just have YT equal to AR of P. I'll zoom out a bit so we can better see this. If D and P are 0, we call it a moving average model of order Q, or MA of Q. If D is equal to 0, an ARMA PQ model will be specified by the number of lags and how many errors. So that's ARMA. There's no integrated component, or there's no differencing. And this table here allows us to kind of visually see some of that. So if P, D, and Q are 1, 0, and 0, we have an ARIMA model, or an autoregressive process of order 1. Those are equivalent to one another. For Q, if Q is the only thing that's non-zero, we have an ARIMA 001. That's a moving average model of order 1, and so on. So you can see how we can collapse down. If there are certain values of 0, we can collapse down to an autoregressive model or a moving average model, or just an autoregressive moving average model. The ARIMA model, or the integrated component, is based on if there's that difference, so where D is not equal to 0. No, so David says no integrated only, 0, 1, 0. So if we were to write out an integrated only model, that would mean that we've got YT minus, actually, let me, if we, and I'll share this with you. And ARIMA, let's say P was equal to 0 and Q was equal to 0. Then what that means is YT minus D is equal to this. So if P is equal to 0 and Q is equal to 0, basically the AR of 0 and the MA of 0, we're regressing on no prior values of Y, and we're regressing on no prior errors of Y. So our prediction is just going to be the mean value, which would be like, I mean, you could do that, but that would be a really bad model because you're just predicting the mean for everything. And that goes back to that naive baseline model that we used on the first, like the morning of linear regression in week 3. So that would be a not great model to do. So we generally do not have just an integrated model because effectively we're just predicting the mean everywhere. And it would be the mean of our training set. And I will drop that here in the chat if you want to see that. So how do we find the right values of P, D, and Q? Generally, we can manually look through plots and do the augmented Dickey-Fuller test. This is the best way to go. This is what you should be doing. Practically speaking, it's less, or it's not incredibly uncommon for people to grid search to find that right difference. We want to be careful because cross-validation is more difficult with time series data. Think about the issues with the train test split that we talked about and how that continues with cross-validation. So it gets more complicated. So you may just like build them on the training set, evaluate them on the test set, and pick the best one in the test set, which can eventually lead to overfitting. But that's something that you might consider doing. So what I have here, I'm going to like summarize this, and then I will unfortunately need to step away. And this is we are now like, we're past the point that the East Coast made it to. And so this is the end of the formal content here. I do want to show you what I mean when I say grid search, but then we'll stop a little bit early. So when I say grid search to find the right difference, essentially I'm setting up this range of for loops. So we're fitting an ARIMA model with our data. We pass in order P, D, and Q. We generate, or we fit our model, we generate predictions, and we can report the MSE. So if we go ahead and run this, we can do that, but we get a value error. And our value error here is the computed initial MA coefficients are not invertible. You should induce invertibility, choose a different model order, or you can pass your own start params. So remember that finding coefficients for moving average model is difficult. I mentioned that there's this academic paper that walks through how to do it. It's advanced, and it's not as easy because it's not something we observe. So the moving average coefficients may not be invertible. So finding coefficients for moving average model, or an autoregressive moving average model, or an integrated autoregressive moving average model, that is going to be difficult and not easy for us to do, or rather for the computer to do. Here's that same paper just tagged again. So this model, a moving average model of order 2, requires us to regress on errors, but we don't ever actually observe those errors. And so this algorithm is super complex. So we can handle this by adding a seasonal piece to our model, which is down below. We can just try and specify a different model and say, we'll skip that, we'll do something different. Or we can try and hack our answer by adding try and except statements. So what is the purpose when we talk about try and accept statements? What is the purpose of try and accept statements? Go ahead and respond to the thread. What is the purpose of try and accept statements? Yeah, it allows us to capture errors. It allows us to handle errors. And so what this will do is whenever we get something like this, we do get a value error, we can ignore it or we can sort of ignore it. So note that we're just hacking our answer here. Errors are telling us that something is wrong, but I'm just saying I'm adding in try and accept statements here. So I'm going to try this, and if there's an error, we're going to pass. But I set up this P, D, and Q, checking from 0 up through 3. You could change this value to be 5, 10, 20, whatever. Obviously, as you grid search, the larger the values you search, the harder it can be, or the more time consuming it can be. But you can effectively have your own grid search over these parameters. So looking at different values of P, D, and Q, we can look at what the best value is for our mean squared error. And granted, this is the mean squared error on our training set, not our test. But as we look at this, 4287. Yeah. So it looks like this model, the MSE for P of 1, D of 0, Q of 3 is 4287. One note to make is that we should have differenced earlier, and we didn't. So we're looking at the actual original data. If you changed D to be something else that included D of like 5 or something like that, where remember, range of 4 excludes 4. So if we run this, maybe it happens to change. Maybe it doesn't. But 4423 is kind of like the thing to beat. So there's additional models down below to talk about seasonal. I mean, we don't have time to do that justice, but effectively there's some code down below that you could use if you want to fit a seasonal pattern to your data. The model name is called it's a seasonal ARIMA model, which effectively says, let's have little PDQ and then big PDQ that correspond to our seasons. The model is called SariMax, and you can fit that here. The reason that X is there is because we have an endog variable, or the endogenous Y variable. But the other cool thing about this is exogenous predictors, or the X variable. This is capitalized on purpose because exogenous is just a fancy term for X variable. So the SariMax model stands for seasonal autoregressive integrated moving average with exogenous regressors model. So you could, if you wanted to lag your precipitation to look at the bus or something like that, you could lag that, and then you could fit that model as well. So the code is here, but that is effectively what we were going to cover. We did not cover it on the East Coast. And so it is not worth our time here to get into that. What I'm going to do is I will, like I mentioned at the beginning of the lesson, I'll clean all of this stuff up, and I will go through and basically do a stream or record a video of this, because I do want you to be able to see seasonal data or seasonal models. I do want you to be able to see exogenous predictors. So I do want to clean that up. I apologize for feeling super poorly. I apologize for, but hopefully you're able to at least see some of this. So to reiterate what I mentioned earlier, this will be the end of anything that you need to see. So you don't need to do anything with the seasonal model. If you say, I hate time series analysis, or I don't want to talk to you or anything like that, then that's totally okay. You don't have to watch it or anything like that. This weekend is very busy, but I will try and find some time to do open office hours in addition to my office hours to cover that for like an hour Q&A session or something like that. And if not this weekend, then I will commit to doing that before capstones in case you want to do this for your capstone. So with that being said, I'm leaving. Have a wonderful rest of your day. I will be back to chat with you tomorrow morning to talk about spatial data analysis. So I will talk to you all soon. Enjoy the rest of your day. Thank you all for your patience, and have a good night. Take care, everybody.